Okay, so in this lecture, we'll be talking about acid-base chemistry, and this will be review for those of you that have had the first 2 quarters of chemistry. This will be review from those classes, and we'll be maybe talking about a little bit of new material that you might not have seen towards the end of the lecture, but most of this lecture will be review. Right? In this class. This is the first lecture of chemistry of the elements, which is sort of a combination of inorganic chemistry and a 3rd quarter of general chemistry. So it's a little bit of a mix of those two. And we'll come across some acid-base concepts throughout this quarter. We've seen these before in the 1st quarter of general chemistry. We did a little bit, and then we took that to the next level in the 2nd quarter of general chemistry in talking about acid-base equilibria. Okay. Most of the questions we'll do, review questions we'll do in this lecture. If you've taken my classes before, you will have seen these same questions, so just be aware of that. They'll mostly be concept-based, conceptual type questions. Not too many calculations. I think there's only one real calculation. Just an overview of maybe the newer material that we'll talk about in this lecture, and that's the Lewis acid-base definition. And that's based on what compounds donate electrons and which accept electrons. It's a third and new definition. We talked about Arrhenius definition, and we've talked about the Bronsted-Lowry definition. The Bronsted-Lowry is all dependent on proton transfer. The Lewis definition is dependent on electron transfer. So a Lewis base is something that donates electrons, and a Lewis acid is something that accepts those electrons. Okay. So where this material is coming from, the 1st quarter of general chemistry, Chapter 4, Section 4. We'll review a little bit of that at the beginning of class, and then in the 2nd quarter we covered sections 18.1 to 18.3, and then 18.9 is the Lewis acid-base definition. Okay, so going back to the first definition of acid bases that we've talked about. That was the Arrhenius acid-base definition, and that's all based on what a substance does, how they behave in water. Okay, an acid, by the Arrhenius definition, is a substance that when it is mixed in water, it dissociates to yield a proton in solution, which then gets converted into a hydronium ion. Okay, so that substance has to have a hydrogen in its formula. And just I've mentioned this before in other classes, but if you, a lot of times you see protons, right, when we talk about acid-base chemistry. When an acid is in water, technically you don't have those free protons by themselves. They become attached to a water molecule and make the hydronium ion. But just be aware that these are really kind of equivalent meanings to them when we're discussing acids, those concentrations. Okay. Technically, if you want to be precise in an aqueous solution of an acid, we really want to know the hydronium ion concentration, but I will always write it for the most part as a proton concentration just because it's easier to write. Okay. Arrhenius definition of a base is a substance that has an OH in its formula and dissociates in water to give the hydroxide ion OH minus in solution. Okay, so by the Arrhenius definition, an acid and a base reaction, what happens is they mix, the acid will give a proton, the base will give a hydroxide ion. Those combine to form water and neutralize each other. Okay. So a neutralization of an acid and base always are going to lead to a salt and a water by the Arrhenius definition. And so our example here, easy example, is hydrochloric acid, sodium hydroxide. When they mix, they form sodium chloride, which is our salt, and water, and they neutralize each other. Right, so strong acids, what are some strong acids? These are the ones you need to know. The halogens, except for fluorine, when they're combined with hydrogen, are all strong. So hydrochloric acid, hydrobromic, and hydroiodic acids. Nitric acid, HNO3. Sulfuric acid, H2SO4. And perchloric acid, which is HClO4. These are all the strong acids, or at least the ones that you need to know for this class. Can really assume that all other acids that you see are weak. Here's another table. Good to point out in this table, there's some weak acids that are listed, like HF, right? That's a halogen, but it's the top halogen in that group, and it's actually a weak acid. Phosphoric acid, and then acetic acid. Anytime you see a COOH, those are going to be a carboxylic acid, and they'll always be weak. We'll talk about those in a minute. Strong bases, right? For a Arrhenius base, a strong base is always going to have OH in the formula, and typically that OH minus anion will be countered with a metal cation. Okay, and then what are weak bases? Well, weak bases are things that have nitrogen in them. So like NH3, ammonia, would be a weak base, and we'll see more examples of them. Okay, so the first question, which of these are strong acids? So think back to that table, try to remember which are strong acids. All right, HCl, yep, that's a strong acid. Phosphoric acid, no, that's not a strong acid. Sulfuric acid is a strong acid. HBr is also strong. Acetic acid is not, right? It has that COOH, which is always going to be weak. If any molecule that has that in it, it's a weak carboxylic acid. And then HF is also a weak acid. It's the one halogen that combines with hydrogen to make a weak acid. Okay, so 1, 3, and 4 are the strong acids, so that would be choice A. Okay, question 2, which are the major species present in an aqueous solution of HCl? Okay, so when HCl, hydrochloric acid, is put into water, what you get out are H plus cations, protons, and Cl minus or chloride anions. Okay, so this is a strong acid. In solution, it dissociates completely. So you don't have any of the combined HCl remaining in solution. It has fully dissociated. And when H plus is in solution, remember you actually are forming hydronium ions with those H pluses. Okay. So the major species present in a 1 molar solution of this, you don't have any HCl left. Okay, so that's not a major species. H2O, yes, because it's an aqueous solution, you have water there. Hydronium ions, yes, you're going to have approximately 1 mole of those. Chloride anions, same with that, you're going to have a 1 molar solution of those. And then finally OH minus, and OH minus is there, but it's there in a very, very small amount. So it's not a major species. So here we have 2, 3, and 4, which that choice would be B. Okay, so on the third question, we have a pH versus a base added on the x-axis. So this is a titration curve. So this is showing a solution of HCl that is being titrated with 0.011 molar NaOH. Okay, which of the following plots corresponds to the same titration but using double the concentration of the base? Right. So what's happening, you're adding base, and as you're adding base, the pH is going to be going up. It goes up only slightly at first, and then it reaches the equivalence point, and it jumps up quite a bit. Okay, so if that base you're adding is higher in concentration, you're going to reach that equivalence point at a sooner. Okay, so it's going to shift the curve this way. So if we look at that down here, the one that's really showing that shift in that direction would be A. Okay, moving on to chapter 18. Okay. So in this chapter, we really introduce the concept of a weak acid and a weak base. Okay. So weak acids and bases dissociate only partially in aqueous solutions. So they're termed weak electrolytes. And we use that double-headed arrow to indicate that. So that's why we covered that in the second quarter when we were talking a lot about equilibrium. Right, so an acid, right, will dissociate in solution and give a proton. A base can dissociate in solution and give an OH minus. Okay. The net ionic equation for a neutralization reaction with a weak acid and a weak base is the same as it is for a strong acid and a strong base. So that's always going to be, when you're talking about that neutralization, that's always going to be the same net neutralization reaction. Okay. So for strong acids, just looking at this graphically, for strong acids, right, like HA, let's just say that's our generic acid. When it dissociates in water, we don't have any HA left. It's fully dissociated into protons and the conjugate base, or A minus. Contrast that with weak acids. For a weak acid, let's say HA is now a weak acid, after we add water or mix it in with water, most of it's going to stay together, okay? And only a small amount is going to dissociate into the H plus and A minus. So weak acids, there's an equilibrium between the acid and the ions, right? So the fully intact acid and the H plus or protons and the what we term the conjugate base or A minus. Right? And that can be described by an equilibrium constant. Right? We can write that equilibrium constant and put the products, concentration of the products over the concentration of the reactants. But since this isn't an aqueous solution, we can assume that the concentration of water is very high and it's not changing very much because it's in great excess. So we can kind of ignore that, and that's what gives us what we call the Ka expression, which is the equilibrium of the weak acid. Okay? And again, it's the concentration of the conjugate base plus the hydronium ion or proton concentration divided by the concentration of the undissociated weak acid. Okay, for strong acids, this Ka value is much, much greater than 1. Weak acids, it's something about 1 or less than 1. Oftentimes, pretty small. Okay, here's some Ka values for some various weak acids. Some of these, it would be good to just have an idea of them. I don't know if I'd really expect you to memorize these formula of them necessarily, but just being able to recognize if you're given especially something with a COOH, that's a carboxylic acid, and that tends to come up quite a bit. Those are always going to be weak acids. Okay. When you compare Ka values, the higher the Ka value, the higher the strength of that acid is. So lower Ka values, the weaker the acid is. The higher the Ka value, the stronger the acid. Okay. Weak bases, in a similar fashion, a weak base is not going to fully dissociate in water. So we have our base here, which is ammonia, NH3. When that goes into water, we can form our conjugate acid. So there's always this conjugate acid-base relationship. So our conjugate acid of a weak base is just when that base accepts a proton. And for this, NH3 accepts a proton and becomes NH4 plus OH minus in solution in water. So that's where that's why this is a base, is because it's increasing that OH minus concentration. Okay. Again, they don't dissociate fully, okay? And we can write an expression for this equilibria, and in this case it's termed Kb instead of a Ka. We can compare relative strengths of acids and bases. So for the formula, if we write the formula of acids here, and we're organizing it from acid strength from lower at the bottom to higher strength at the top, the conjugate base of the acids are then shown on this side. So for the stronger acids, so the stronger the acid is, the weaker the base is for the conjugate base, and vice versa. When you have a very weak acid, that conjugate base is going to be very strong. Okay, so let's try another practice question or review question. Classify each of the following compounds as a strong acid, strong base, or weak base. Okay. And then write the Ka expression for any weak acid. Okay, so for A, this is A is a strong base, right? Because it has an OH in its formula coupled with that potassium. So in solution, that dissociates and gives a much higher concentration of OH minus. Okay, for B, this is an example of where we have a COOH, that is a weak acid. And maybe this is a little bit confusing. It could be because it has an OH group in it, but that OH group is not able to dissociate into solution because it's actually COOH, which is this structure. This is our carboxylic acid, right? And that can be attached to any number of things that I can abbreviate as an R group. And this is the proton that it can lose. So when it loses that, it becomes COO minus, gives up that proton, which then raises the proton concentration. That's why it's an acid. But it is a weak acid because this does not dissociate fully. Okay. So we can write our Ka expression for this one. Right? We have CH3 2 CHCOOH. Don't really care about most of this. All we really care about is that last hydrogen. Okay, in water, I guess I should show the water there, plus H2O when we combine that with water. Okay, what happens is it can dissociate into CH3 2 CHCOO minus, and water will then pick up that proton and make H3O plus. Okay, so our Ka expression is just going to be the products over the reactants, so H3O plus our conjugate base, which is CH3 2 CHCOO minus, divided by our fully intact undissociated acid, CH3 2 CHCOOH. Go. Okay. H2SeO4, this is a confusing one. This is actually a strong acid. It's like sulfuric acid, but instead of sulfur, you have selenium. Wasn't on the list of strong acids that we mentioned earlier, so that can be a little bit confusing, but on an exam I wouldn't include that one on a problem like this, so don't worry too much about it. And then finally, we have a weak base at the end. This is a weak base because that NH2 group there and that organic molecule, that those nitrogen groups make weak bases. Okay. All right, next question. Examine the Ka values for the acids shown below. And we have a list of 4 of them. Okay, and we're considering 0.1 molar solutions of each acid and arranging them in order of increasing H3O plus concentration. So what that's saying is essentially we're going to write them in order of increasing acid strength. So remember what that Ka expression is. The bigger number for Ka means you have more of the products being produced, so it's dissociating more, so that means it's going to be a stronger acid. So if we just rank these, looking at the size of Ka, the biggest Ka here is going to be formic acid, that'll be number 1, then acetic acid would be number 2, hypobromous acid 3, and phenol 4. So that's the order we're going to need to look for in the choices, and that choice here would be choice B. Okay, finally review question 6. What are the major species present in an aqueous solution of 0.1 molar CH3COOH? Okay, so this, again, is a weak acid, right? We have a carboxylic acid there. Okay, so this is similar to a question that we had previously with question 4, but instead of a strong acid, now we have a weak acid. So remember, weak acids don't dissociate very much at all. So we can consider if we have a 1 molar solution concentration of this acetic acid, we're not going to have much of it dissociated, so that's going to be present in about 1 molar concentration. So 1 would be present as a major species. Again, it's an aqueous solution, so water's going to be there. Being a weak acid, it is an acid. It's going to raise the H plus or hydronium ion concentration, but only slightly, right? Because it's weak. So this is not going to be a major species, although it will be there. Same with OH minus. There's always some OH minus in aqueous solutions, but again, not very much at all, because this is 1, it's an acid, and 2, it's a weak acid. You're really not going to have much of that. And the conjugate base, the dissociated form of it, that's not going to be there in very much at all concentration, because again, it's not dissociating very much. Okay, so the correct choice here would be 1 and 2. Okay, moving on to section 2 of chapter 18. This is where we talked about the autoionization of water. And that's how water by itself will undergo what's known as autoionization, where one water molecule can pick up the proton from another water molecule and form an H3O plus, so sort of like an acid, and then the water that lost a proton will be an OH minus, so that's sort of like a base. Okay, so water can kind of undergo this by itself. Right, we can write an equilibrium expression for this, right? And when we write that, those concentration of water, again, since it's an aqueous solution, it's not really changing much. We can ignore that. And that's where we get this expression that we call Kw. And W you can think of as standing for water or autoionization of water. It's going to be the concentration of H3O plus, or H plus if you prefer to think of it in that way, multiplied by the concentration of OH minus. And it turns out that always equals 1 times 10 to the minus 14. Okay. So this ultimately is where we get our pH scale. Okay, so in the absence of other acids or bases, this H plus concentration is going to equal our OH minus concentration. So they're going to, using that Kw expression, you can calculate them. They'll both be 1 times 10 to the minus 7th molar. Okay, again, that's in the absence of any other acids or bases. So a completely neutral solution. Okay, a change in the H3O plus concentration is going to cause a change in the OH minus concentration, right? And they'll be inversely related. Okay, and you can tell that because of that Kw expression. This one goes up, this one has to go down because the product of them always has to equal 1 times 10 to the minus 14. Okay. So higher H plus concentration means lower OH minus. Higher OH minus means lower H plus. Okay. So in that sense, this is how we define the terms acidic and basic. Right, so in acidic solution, you have more hydronium ion or protons than you do OH minus. In a basic solution, you have less H3O plus or H plus than OH minus. Okay, neutral means they're equal. Okay. Right, so if you want to, this chart just shows you how to convert from one to the other. You know, if you want to know the H3O plus concentration and all you're given is the OH minus, you divide into Kw. Okay. So the next review question is something that we really haven't mentioned yet, but I think all of you probably know what this is, this pH. Okay, so which of these three solutions would have the highest pH? You have a 10 to the negative 3 molar solution of NaOH, 10 to the minus 6 molar solution of sulfuric acid, or 10 to the minus 12th molar solution of HCl. Okay, so what does high pH mean? High pH means basic. Acids give lower pHs. So in this case, we only have one base, and that's NaOH. So the solution of NaOH is going to have the highest pH. And just to remind ourselves what the pH scale is, it's shown here from 1 to 14. Okay, and this is based on that log number is for the exponent on 10 in the Kw expression. That's really what this is based on, why it goes from 0 to 14. Okay. Anything at 7 is where we consider that to be neutral. Anything below that is considered acidic because, again, the H3O plus concentration is outweighing the OH minus concentration. Anything above 7 is considered alkaline or basic because OH minus now is in a higher concentration than H3O plus. And again, at 7, pH 7, they are equal. The expression for pH that's important to remember is pH equals negative log of the H plus concentration. Or again, more accurately, hydronium ion concentration, but I find it easier just to write H plus. Yeah. You can write a term for what's known as POH as well, and that equals the negative log of the OH minus concentration. Right. So if we have our Kw expression, which we've written before, you take the log form of Kw, right? If you take the negative log of Kw to get essentially what would be a pKw, that's going to equal minus log of H plus times minus log of OH minus, which is, again, pH and POH. So pH plus POH has to equal 14. So this is another good relationship to remember, right? You can remember it in this form, Kw, or the pKw form, which is maybe a little bit easier to deal with. pH plus POH equals 14. Okay, so let's try a question using this calculation. Calculate the pH for a 0.05 molar HCl solution. Okay. And remember, this is our equation we're using. So all we're doing in these is just plugging and chugging, right? H3O plus or H plus concentration in this case is just going to be whatever the concentration of our strong acid is, right? Because it's fully dissociated. So if we have 0.05 molar solution of HCl, it fully dissociates, and that becomes a 0.05 molar solution of H plus. Right, so pH is just going to be minus log of 0.05, which is 1.3. Another way to make a question like this maybe more difficult is then asking, okay, what is the pOH of this solution? Right, and for that, you need that relationship, pOH plus pH equals 14. So pOH would be 14 minus pH. So 14 minus 1.3 would be something like 12.7. Okay. So being able to calculate a pH is important, but then also being able to work between pOH and pOH and pH, or work between a hydronium ion concentration and a hydroxide ion concentration. Being able to convert back and forth is important. Okay, our last sort of review question or review section is section 3 in chapter 18. Okay, and this is where we introduce the Bronsted-Lowry definition of acids and bases. So in this definition, an acid is something that is a proton donor, gives up a proton. So much like Arrhenius definition, an acid has to have a hydrogen in its formula. Okay. A base is a proton acceptor. Okay, so that's any species that accepts an H plus ion. So really for this, it expands the definition of what a base is, because a base in Arrhenius definition had to have an OH in the formula. This doesn't have that. All the Bronsted-Lowry definition states is that it needs to be able to accept a proton, and to do that it has to have a lone pair of electrons. So anything with lone pair of electrons will be able to accept a proton, which is why for weak bases, you see compounds that have nitrogens in them, because nitrogens have lone pairs of electrons. Okay. So in this definition, an acid-base reaction is a proton transfer process. And this is the figure the book uses, right? So if we have HCl and water, right, we have a proton transfer. The proton goes from HCl, which is our acid. Okay, that's our proton donor, it's our acid. And that proton is transferred to water, and because water accepts our proton, it's our base. Okay, and water it can accept that proton because it has a lone pair of electrons to do so. Right, and NH3 ammonia has those lone pairs of electrons. Right, remember it's a weak base. It can accept a proton from something like water, right, and become NH4 plus, which gives OH minus. Okay, which is why this is a base. It's increasing that OH minus concentration. And using the Bronsted-Lowry definition, this is where we come up with the terms conjugate acid and base pairing. Okay, so for this, in the forward reaction, H2S is going to HS minus. So in the reactants, H2S is our acid, NH3 is our base. Right? When this does donate a proton, it becomes HS minus. And when this accepts a proton, it becomes NH4 plus. So if you look at those in the reverse direction, if the reaction was going in the reverse direction, right, NH4 plus would be our acid and HS minus would be our base. So our acid in one direction becomes our base in the opposite direction, and so forth. And that's where we get this idea of an acid having a conjugate base and a base having a conjugate acid. Whatever the formula of those are, it's what happens after the proton is transferred. Okay. Right, so that's where we talk about these conjugate acid-base pairs. So H2S and HS minus are a conjugate acid and base pair. Okay. So in the Bronsted-Lowry acid-base reaction, this is where an acid and a base react to form a conjugate base and a conjugate acid. Right, and here's an example of some conjugate acid-base pairs. So our acids are shown here, their conjugate bases are shown here. So all a conjugate base is the formula of your acid when the proton is removed. So our acid, in this case HF, when the proton's removed, what do we have? That's F minus. That's what's left. Okay, so that's what would be our conjugate base. And our bases, the formula for a base with the proton added to it would be the conjugate acid. So H2O here is acting like our base. It's accepting our proton. When it does so, it becomes H3O plus, which would be considered its conjugate acid. So let's try a problem with this concept. Right? Identify the conjugate and acid-base pairs in these two reactions. So first, we need to look, what is our acid, what is our base? So in number A, or letter A, H2PO4 is what's donating a proton to CO3 2-. So here is our acid, and this is our base. So our acid, when it gives up a proton, becomes HPO4 2-. So this is what we would consider our conjugate base. And that's another way you can tell is because in the reverse direction, it's going to be acting like a base. It's going to be accepting a proton. Our base now becomes HCO3-, which is its conjugate acid. And bottom reaction, we have water and SO3 2-. Water here is acting like a base, an acid. It is donating a proton. And OH- now becomes our conjugate base for H2O. And SO3 2- is our base, becomes HSO3-, which is our conjugate acid. Okay, moving on to our last section in chapter 18. This is where the Lewis acid-base definition, the third and final definition of acids and bases, is introduced. Okay. So in the Lewis definition, a base is a species that donates an electron pair to form a bond, and an acid is a species that accepts an electron pair to form a bond. So in Lewis definition, we're talking about electrons, right? Bronsted-Lowry, we're talking about protons. The donor is an acid, the acceptor is a base, right? A proton's a positive charge. In the Lewis definition, we're flipping that and talking about electrons, right? And so electrons is the opposite sign, right? It's negative, an opposite charge than a proton. So our definition is sort of opposite, right? In the Bronsted-Lowry definition, right, what donates a proton's an acid. In the Lewis definition, what donates that electron pair, or that negative charge, is a base. Okay, so our donator here is a base, or an acceptor is an acid. Right, so the Lewis definition views this acid-base reaction as the donation and acceptance of electrons to form a covalent bond. Right, so what are we looking at in terms of Lewis acids and bases? What do their formula look like? What molecules or elements are involved in this? Okay, so a Lewis base, because it's donating electrons, that means it has to have those electrons to donate. So it has to have a lone pair of electrons. So any substance that is a Bronsted-Lowry base is therefore also a Lewis base, because remember, Bronsted-Lowry bases accept a proton, but to do that they had a lone pair of electrons. Right? Well, if they have a lone pair of electrons, they can also donate those electrons to form a bond, so they're also Lewis bases. Okay, a Lewis acid must have a vacant orbital, right? Or be able to rearrange its bonds to form one, and it needs to have that to be able to accept that pair of electrons to form a bond. Right, and this really opens up the spectrum of what an acid can be. Okay, so things that don't necessarily have a hydrogen in their formula can be still considered acids by this definition. Okay. So here's a good example of a Lewis acid-base reaction and some things that can be Lewis acids. So electron deficient molecules can be Lewis acids. So something that a molecule where it's an atom in that molecule doesn't have a full octet. So something like BF3, this boron, right, has only 3 bonds to it, so it has an open orbital. And because of that, it can accept a pair of electrons, in this case from NH3, from that nitrogen in NH3, and you can form this bond. So you have an acid, a Lewis acid, that accepts the electrons, a Lewis base that donates them, and when they react to form this compound, that's what's known as an adduct, or a Lewis adduct. All right, and we're forming a covalent bond. You can have a case where you have Lewis acids that have multiple polar bonds, so something like SO2 can act as a Lewis acid and accept electrons and form an adduct there, in this case with H2O. Okay. The other main class of Lewis acids that you commonly see are metal cations. Right? Metal cations, they have a positive charge, and they can accept electrons from any number of substances. Right? In this case, water. Right? You put a solution of like a salt in water, you get a metal dissociating from the anion it's in, and it gets coordinated by water molecules, right? And that's making a Lewis adduct, right? And the metal is acting like an acid, and the water is acting like a base. You see these in nature as well. So in chlorophyll, the magnesium ion acts as a Lewis acid in chlorophyll. It's able to accept electrons from the nitrogen groups in this porphyrin heme type molecule here, and that forms these bonds to magnesium, and that makes the Lewis adduct. Something that we'll see in this class sort of regularly when we look at coordination chemistry, you have your metal ion, a cation, and it will be coordinated by any number of different compounds. So something like this, right? In this case, the ACAC is just this molecule, right? And you have these 2 oxygens on it. Those oxygens have lone pairs that can coordinate around that center cobalt metal and form these adducts with it. So in this reaction, your cobalt is your Lewis acid, and the ACAC molecules now are your Lewis base. So we'll see lots of this in the lectures to come, dealing with coordination chemistry and metals. Okay, so let's try some practice questions. Identify the Lewis acids and Lewis bases in the following reactions. So in the first one, we have H plus OH minus going to H2O. So this would be like a classic acid-base neutralization. Right, so remember, it's easy for us to just say, okay, H plus our acid, OH minus is our base, but let's try to think about it in terms of that Lewis definition. Okay, in the Lewis definition, our base is what's donating the electrons or the negative charge. So our Lewis base would be our OH minus, right? It's donating electrons, and our H plus is accepting those electrons, so it's an acid. Okay, the next reaction is Cl minus plus BCl3 going to BCl4 minus. Okay, again, our base is donating electrons, so Cl minus in this case is going to be donating our electrons to that electron deficient boron in BCl3, and it's acting like an acid because it's accepting those electrons to form that adduct. And finally, we have a metal ion reacting with water, so our water is going to be our base donating electrons to our positively charged metal, which is our Lewis acid. Okay. The last thing we'll talk about, and this is new material, I'm pretty sure for everyone. I did not mention anything about this in the previous class, and I don't think any of the other instructors did as well, but it's the hard-soft acid-base theory. And what I don't like about this is you sort of have to memorize more stuff. So I'm not going to be testing you strictly on knowing, iron is an intermediate and vanadium is a hard acid. On a question like this on an exam, and we'll have a couple practice questions using this concept, but I'd probably tell you what each species is. Is it hard or soft, relatively speaking? Okay. What I do expect you to know, though, is how hard and soft things react together and how do they form stronger bonds, what combinations would make stronger bonds, and then the types of things that are considered acids and the types of things that are considered bases, right? So acids are going to be metals, right? Lewis, in the Lewis definition, those are going to be what's accepting our electrons. And our bases will be nonmetals because they'll be the things that donate those electrons. Okay. So that being said, what is the hard, soft, acid-base theory? Well, the theory states that soft acids are going to form stronger bonds with soft bases, and hard acids form stronger bonds with hard bases. So if you have a strong acid, it's going to form a stronger bond with a soft base. If you have a hard acid, it forms a stronger bond with a hard base. So hopefully that should be pretty easy to remember. Okay. Hard prefers hard, soft prefers soft. Right. This is an empirical theory, which means there's nothing. You can't just look at the periodic table and be able to tell that. Okay, it was done through experiment. That's how people discovered this, and that's what led to this the classification of being hard and soft. So that's one of the reasons I don't like this too much, because it's not something that you can just look at the periodic table or look at the electron configuration of of one of these and to be able to tell that necessarily. Okay, which means you just kind of have to memorize this stuff. But again, I'll try to make the questions. I will tell you whether the metal is hard or soft, or whether the non-metal is hard or soft if I give you a question like this. Okay. There's some general trends that you can see for hardness or softness. Okay, so for acids, hard acids, the formation constant has the order of, in this case, iodine is less than bromide, is less than chloride, is less than fluoride. So the formation constant for hard acids is going up as you go up a group. Okay, for soft acids, and that's with these bases, the halogen bases. Okay, and for soft acids, the formation constant shows that complexes are more stable in the reverse order. So the formation constant's getting bigger as you go down that halogen group, right? So that means, what does that mean? That means you're getting, right, softer is, a soft acid's going to want to form, the formation constant's going to be higher when it's forming an adduct with a soft base. So if it's getting higher as you're going down a group, that means softness is increasing down a group or hardness is increasing up a group. Okay. Right. Many acids are kind of borderline, being between hard and soft, which makes this theory even harder to use. But again, in this class, we're just going to be focusing on the things that we'll just call something hard or soft. We won't really need to make that distinction of intermediate. Okay, here's a table of things that are hard, either acids or bases, and things that are soft. Okay, these are the borderline. We won't really concern ourselves with too much. Okay, so the nature of the adduct that's being formed here. A hard acid and a hard base adduct tend to have more ionic character. So when a hard acid and a hard base react, that tends to form more of something that we'd consider an ionic compound. When you have a soft acid and a soft base making an adduct, these are going to be things that have more covalent nature. So if we look at the periodic table, if we look at just a small section of the nonmetals, hardness is going to be increasing as you go from left to right and as you go up a group. Okay, so fluorine here is going to be the hardest base. Okay, the opposite is true as you go down a group or as you go from right to left, softness is going to be increasing. So here that would be arsenic, and just in this small little bit that we're looking at, that's going to be the softest. So that's just a general trend we can kind of look at. Here we have an example. If we're combining silver with different halogens, and silver is actually a soft acid, right? That silver, when it's combined with fluorine, which is the hardest base, we get a pretty large solubility number, just at least relative to the other compounds. So it has the highest solubility product, which means it's the most soluble, which means it has a weaker bond between the silver and the fluorine. As you go down that group, each of these is getting softer and softer as a base. So the iodine, which is our softest base here, that solubility product gets smaller as you go down, which means it's more insoluble, which means that bond you're forming is more and more soluble. More and more strong, and it becomes less soluble. And that's because you have more and more this soft acid and soft base. You're getting more covalent character, and it's not going to dissociate in water. Okay. The linkage site matters on this. If you have a molecule like SCN here, one side, the nitrogen, will be harder, the sulfur side would be softer. Okay, so if you have different acids, right, the chromium is going to be harder of an acid. It's going to want to bond to the nitrogen, preferably, preferentially. All right, hard likes hard, soft likes soft. So a platinum, which is a softer acid, would tend to bind more to the sulfur side. Okay, so let's try some practice problems. Okay, in this hard-soft acid-base theory, we can use it to predict solubility trends. Based on the determination of the hardness of the ions, what happens when AgF and lithium iodine are placed together in solution? Okay, so AgF, if we just write this out, we have AgF minus plus lithium plus I minus. Okay, so you take the cation from one and combine it with the anion from the other. And it turns out that, silver is, more soft than lithium, so relative, silver is going to be soft, lithium is going to be hard. It's opposite for the anions. Fluorine was hard, and iodine is going to be the softer. So this will be, let's just call this soft. Okay. So what that means is our silver and iodine, since they're both soft, are going to preferentially bind together to form AgI. And the two that hard acid, hard base, would be lithium fluoride, would sort of combine together. And they would combine together, form strong bonds that are harder to break, and ultimately create precipitates. Okay. Last practice question, will mercury form a stronger compound with iodine or fluoride? So to know this, well, we need to know mercury. So on an exam, I'd rewrite this question to say, will mercury, parentheses, a soft acid, form a stronger bond with iodine or fluoride? And then you'd have to kind of remember the trend here, right, in the halogens, and that's the hardness goes up as you go up the group, or the hardness goes down, or the softness goes up as you go down the group. So fluorine is going to be the hardest base out of that, and iodine would be softer. And if mercury is soft, it's going to preferentially want to bind with iodine. So the you're going to make a stronger bond with iodine than you would with fluoride, because mercury, again, is soft. Okay, so next time we're going to move to chapter 23, and we're going to start discussing transition elements. And this really is where we start into inorganic chemistry discussions.